Hold on, it's January the 19th. All right, so we need to talk about yesterday's problem. I did it again today, early in the morning. When did I submit it? 8 hours ago. So, really not that early, 11. So, what? I read the solution. Okay, I read the solution, and I was able to figure out. And of course, the way I do it is slightly different from the solution. But I want to recap how this whole thing got solved. So what I was trying to do yesterday was to extend this from the 2D, right? We have a 2D problem number 47, which is number 47. Oh, it's not 47. It's 42. My bad. The number 42, right? I was trying to extend from this problem. So this problem is 2D, right? And you're trying to find how much rainwater you can trap. And the solution for this, at least a good solution, right, is you go 2 pointers and then you'll find the uh, maximum on the left, the maximum on the right. You pick the smaller one and then you start going that way. And every time you find a height that's smaller than the smaller of the two borders, basically you're just going borders, right? Because the border is on the left and border is on the right. And you find a smaller border and your current height is a difference between the smaller border and U will be the amount of water you can hold at that time. That was essentially the solution. But the main thing is when I was reading through the solution, I kept having this idea of, okay, we have a max, like two maxes on a border, and we try to find a small one. I didn't really connect how this can be extended into 3D, right? Into 3D. And the way I extended was to go row by row using the same method, and then go column by column using the same method, and I'll update. But that is not the way to do it, because the key, right? The key here is not about the row or column. The key here is you will find the border. You will find the border with the smallest maximum height. That is the key, right? That is the key. And then here, the border happens to be on the left hand side and the right hand side. It just happened to be this, right? And you just go from both ends coming in, and you look like it looked like a 2 pointer problem, but it's actually not. All right, the essence is not 2 pointer. The essence is we're trying to find the smallest height of the border at the moment. That is the point. Okay, that is the point. You find the smallest height of the border, and that determines, at least at that time, what is the highest water level it can be. And then whatever cell you encounter that has a smaller height than the current smallest border height, then you find the amount of water that can be accumulated above it. And that is the exact mindset you have to use for this problem, because you turn it into 3D, right? You turn it into 3D. The principle does not change. You're still going through borders, right? You want to find the borders and then find the smallest border among them all, right? And you start from there. Now, for here, when you find the smallest border, to get to the next cell, which is like adjacent to the border, you just move the pointer left and move the pointer right. But here you can, there's no left and right. Therefore, here is where the BFS comes in. You have your current cell, like in this case, like this is having the lowest border height. And then you need to find the next cell, right? The next cell that is adjacent to it. And then you work from there, right? And if the next cell has the smaller border than you, because your current is the smallest border, the next cell has a lower height than you, then you have the amount of water you can accumulate. Now, the border for this grid to start with is essentially the outer edge. Therefore, you need to go through the outer edge and then find the smallest height of the outer edge, right? And then from there, you can start, BFS, and all the outer edges are considered visited, right? And you go for the cell that has not been visited. And if it's higher, you want to keep it, because who knows, maybe that height will be used in the future, right? So you need to save this. If it's lower, then you find the amount of water that can be held. And then here's the trick. You have to put that into it as well. Now, the reason you put that into it, actually, I just realized you don't have to put that into it. You don't. You absolutely, no, you do. You put that into it, right? You put that new height into it, but you will not use the cell height. You will use the current water height because you're extending, right, the minimum border height into the current cell. You're extending it. So you need it to be the same height. So we know, like, kind of you go from the border, you're going in, and eventually you also need to, every time, to pop up the smallest height currently. Therefore, you need a min heap for this. That's why the hint for this problem, I mean, it doesn't, not hint, the topics for the problem, you have a BFS and you have a heap. That's why. And then you can see here we have a priority queue, right? We have a min heap, and this is just the directions, and then we put the edges, right? We put the this is top row, bottom row, put into it, and whenever we put into the heap, we consider the cells visited, and it will put the first column and the last column into it as well. And then what you do is just to go through the whole thing. You just pop the heap right on the top, so you get a smallest height. You grab the height, and you grab the cell, and you go for directions. And you go for directions, you make sure that the next direction has not been visited. And if the current height of this new cell you're going to visit is smaller than the smallest border height at the moment, then you accumulate the water, and then you put this new height. Look at here, we do maximum, which means it's either going to be h, which is the current lowest, or going to be the height. That's the next cell you're going to visit. Here you put that into the heap, right? And you mark it as visited, and you decrement on the remaining, right? And then you just do this, and then when you're done. So when you look at this, it is indeed not that complicated. The most important insight is to translate, to extend the 2D problem into the 3D, and that actually requires a much deeper understanding of this rainwater trapping problem. I think for the past, I don't know, when did I first do the rainwater problem? I think I first did a rainwater problem in 2018. So for the past 6 years, I've done this problem many times. The total submission standing at 27, and you can see almost I do this almost every year, right? 2018, and then we didn't do it in 19, but did in 20, 21, 22, 24. So repeatedly, I do this problem. I know the solution, right? There are two solutions for this, but I think right now is the first time I can say I fully understand the principle behind it. And the principle is border. Border is the principle. It's not about monotonic decreasing array. I mean, that's kind of why, and I mean, I remember doing an interview for Microsoft, and they used this problem verbatim, and I was not able to give a good argument. Like, I just keep confusing myself, because at that time, I just really didn't understand. Like, I knew the solution was a monotonic array. I kind of remember there's a two-pointer solution, but I never really understand the truth, right? The real principle behind it. And the real principle behind it is border. You are just finding the current lowest border. That's it, nothing more. In fact, if you want to do this problem using the method that we just saw, right? BFS plus priority queue, you absolutely can do it. It's definitely you can do it. It's the same principle. And that principle can be extended if you want to do rainwater trapping in 4D. Right? Lord knows what that means, but if you want to do in 4D, you can do it. You can do it in n dimension, right? All you need to do is find the borders, right, and then find how the next adjacent cell is found, and then you can run it, because the principle is exactly the same. Yeah, sometimes it happens, right? It happens. Like a problem you have done many times, and you knew how to solve it, or maybe you memorize the solution, but yeah, that's not really enough. What is required is to understand the principle behind it. And then for the rain trapping water, the principle is and has always been finding the lowest border, because that is what determines how high your water table can be. So it's a tough question, but only because I didn't very well understand how this whole thing goes. Now, it is interesting that my solution stands at 179. I think this is the fastest I get. But you look at this, some people can score so high. I don't know how they do it. It looks about the same. They have visited, they have priority queue. I don't know. But it also depends on when this was done. It could be as time goes on, they increase the number of test cases. That's also possible. But that's it. That's it. I just want to go through this. I think it's very important. Hopefully I can remember this, right? Hopefully I can remember this. And so next time when the similar problem pops up, then I will be able to... Actually, I don't think there will be a similar problem. If this type of problem happens again, it will be exactly the same. Because I don't think it will be tested on, like, say, 4D, right? It will be either 2D or 3D. All right, anyway, let's get on to this one. First, complete a painted row or column. So given a zero-indexed integer array, all right, and an m by n integer matrix, so we have a matrix as well. Array and map both contain all the integers. So they both contain all the integers in the range 1 to m times n. Go through each index I in array. So we go through each index I in array, starting from index 0, and paint the cell in mat containing the integer array I. Return the smallest index I at which either a row or column will be completely painted in the matrix. Okay, so this is the order that they're going to be painted. This is how the matrix look like. And it will contain exactly, there will be no duplication in the number. So in this case, the first painted is 1, second painted is 3, the third painted is 4, and the index, so the smallest index is 2, so 0, 1, 2, you got a row or a column. How is it? That's great. I forgot to close the door. Was cold? All right, so the second example, you first go here, and then you go here, 7, and then 4. All right. So the first row or the first column is painted. I mean, painted just means they got visited, right? So basically, array is the order, and we can convert array into a list of positions, coordinates, so you know which one will go next, right? So we have to go through array, we have to go through the order. We just need a very quick way to decide whether when you do the current painting, whether your current row or column has all been visited. How do we do that fast? Okay, and based on what I see, we probably have to do this either in O log mn, or O1. So how do you tell whether a row, your current, so when you paint yourself, right, the only row or column that can be fully painted is your row or your column, right? So how do you, we can keep track we can keep track of the rows and columns. Like on this row, how many has been painted? Yeah, I think that is not a bad idea, right? We keep track of how many cells have been painted. So this row or this column. So we imagine we have M, we have all rows. Okay, we have an array for all rows, and we have an array called all columns. And every time a cell is visited, we'll update that row and column by +1. So we say one more has been painted there. And then we keep going until that one become M or that one become N. Okay, I think this problem has been solved. Now, can we do the visit smarter? What do you mean by smarter? What I mean is, can we I don't know. I don't really know. I think we can do something like this. An array of array, right? An array of array, and 0 doesn't really have anything. But starting from 1, it can be this, like in this case, 1 would just be 0, 1, right? We can put 1 at 0, 1, 2 at, my bad, 2 is 0, 1, 1 is 1, 0, right? 1 is 1, 0, 2 is 0, 1, and then 3 is 0, 0. Like we do this, right? We do this. Now we go through array, we directly look into this. Think that makes a lot of sense. Okay, let's do this. So we need some auxiliary. We need some auxiliary array for this. All right, let's do this. So first things first, what we need is a vector of int. I call it positions. Okay, positions, and it's going to be, let me also do this. Should be mat dot size, and n should be mat 0 dot size. Can it be 0 in length? No, that cannot. Okay, so the positions will be actually it should be m times n, right? That is the total length, actually +1, and then we need, everything will be std vector of int size 2. Okay, and now we're gonna go for int a of array. That's actually not true. We're gonna go through mat. So I0 I smaller than m I plus. So I have to go through the whole thing for int j0 j smaller than n j plus. So what do? We say positions mat I j 0 equal to I, positions mat ij 1 equal to j, right? So we fill the positions, and then what we're gonna do is just go through. Oh, we also need cell count, right? Cell count row. This will be size, the first row, second row, so m. Okay, and we'll do the same thing. We call it cell count column n. all right? And we say for int a of array. Now we know the positions, okay? We know the positions. So we say cell count row, right? Cell count row positions a 0, right? So that row plus plus, and then cell count column positions a 1, that one plus plus. If cell count row you know what? I think it'll be easier if we just go I equal to position A 0, J equal to position A1, right? And then here we can simply just do I, and this we can simply do J, right? And then we just say this I value is equal to n, because for a row to be filled I need n, or cell count column J is equal to n, m, right? Column. Then we will return what? I cannot even use that. K equal to 0, K smaller than array dot size, and K plus plus, and A is equal to array K. You know what? A only uses once, so I can just do array K here. Right, and then I do array K here. So once it's done, if this, I will just return K. And we say return -1 should never reach here. All right. Let's see if this one's right. Looks good. All right, this one looks good. So I do think that's it's pretty much the solution. So this is 2661. First, right, we record the positions of each value in array, right? The matrix positions, right? The matrix positions of each value in array. Then we use two counters to keep track of the number of cells that have been painted on each row and column. As we go through the values in array, right, in array, we use the position matrix to find the ij, right, find the ij and update the count of painted rows, the painted cells in the ith row and jth column. Once one of them shows that the entire row or column has been fully painted, we have found the answer. So it will run in OMN. Alright, we're gonna run the test one more time, and then we're gonna submit it. Alright, submit it, see how it goes. Alright, I think it goes pretty well. I believe the last time I submitted probably also one shot. 2023, yeah, 2023. Alright, what's our 104? It's alright, 104. .26%. Alright, let's read the editorial. What does the editorial say? Brute force. What's the runtime of brute force? That is brute force optimized with counting. I think this is what we use. Yeah. I can read through this really fast. Well, this row count, column count, unordered map, num to positions. So instead of using an unordered map, we're using vector of vector. It's essentially the same thing. And then the first they will store the positions. That's exactly the same as what we do. We can do it that way. I wonder if we can do it that way too. I want to try. Basically, I say this shall equal to ij. Is that allowed? Well, you know, it does allow. Now I have another question. Does this one? Oh, hold on. Okay, this probably we're pushing it, but I want to try. So can I say auto ij equal to positions array k? Is that allowed? Nope, that is not allowed. We cannot decompose it. I don't know, how do you decompose? All right, this is a good question. C++ decompose vector. You cannot decompose a vector. Okay. Multiple vector, split vector into multiple vector based on a certain criteria. Even, odd. That's useless. Oh, I guess I checked this question before, but tuple array, it's not possible with vector. Yeah, I guess it's because vector, even if you define how large it is, you still cannot do it. Yeah, that's fine. That's fine. I'm just curious. So this is not allowed. But this is allowed. Now I don't think this will make it any faster or anything, but it's good to know. Right? And then they go through this thing. They go auto. Why can they do that? Because they use a pair. Oh, so you are telling me that if I don't use the vector, if I use pair, holy crap, this might actually work. So we do that, right? It's a pair. And then when you're coming here, we also use a pair. We say auto ijs equal to positions array k. And this will work. It does not work. Why? No matching constructor. Oh, that is not right. Oh, that is interesting. Can I just not do this? Right, that I think I can do that. I just say we have n plus times n plus 1 count. Okay, let's try. See if this one give me a faster, because I use pair. Dude, you should use pair. You should start using pairs. Look at this. Look at this. Look at the amount of time saving. We went from what? 104 milliseconds to 3. 104 to 3. The only thing changes is instead of using a vector, we're using pair. Dude. But hold a sec, can I have 3 elements in pair? Element in pair. Is that possible? Oh, you are nesting a pair. Oh, that is actually pretty smart. Well, Gemini is pretty good in doing this type of thing. See, this is what AI helps speed up your programming. It's not like it programs for you. It just saves you time to read through the documentation. You ask a question and it tells you the answer directly. You use tuple. You use tuple. I see now. Okay, I'll start using this more often. It's definitely a better one. Yeah, let's record this. Use pair to significantly, right, improve runtime. The runtime dropped from what, 104 milliseconds, right? 104 milliseconds to 3. This is absolutely bonkers just by that change. Yep, this is what I'm going to use. It's like you do vector for vectors, always a safe option. But for things that you know is only 2 or only 3, yeah, you really should not use a vector. You should use a pair. But anyway, this is exactly the same, right? Oh wow, they even say the same thing as what I said. All right, what is this one? Reverse mapping. The time complexity is about the same. Reverse mapping. Let's just read the code. Maybe it will help us understand. So this is still mapped to store the index of each number in the array. Reverse mapping. Hold on. It's just int to int. So number to index. So every value in array, we map it to an index of array. And rows of column, check for the earliest row to be complete painted. So you go through row, track the greatest index in this column. Last element index. So now you go through the column and you get its index because you have a reverse, and you got the latest index. So basically this is saying if I go through like the first row and what is the latest index is needed, and the result will be the minimum of them. Okay, I see that. Check for the earliest column to be completed painted. So you go to column as well, and then you return the result. That's, yeah, it is a reverse mapping. So our method is we go through this array and it will count which row or which column first reaches the target. But the reverse mapping is we go through the matrix. We just go through the rows, all right? And as we go through the row, we check this array to see what is the biggest index, right? Which is the biggest index encountered as you go through a row, that you know at which index this row will be painted. So you go through all the rows, you go through all the columns, and you can find their indices, and then you return the minimum of all of them. It's the same, but I think it does use a little bit less space. I mean, for one, you don't need a count, right? You just need a map for the positions, and then that's it, right? You just need that. You just need those two. You need a count. No, you don't need a count. You need a mapping, and that's all that is needed. Saves space. All right, that was good. Right, that was good. So supposedly we should do this, but don't feel like it, I'm gonna call it a day. But we know how this one is solved. Basically, we just need to do a segment tree. Yeah, I know, segment tree. One of my least favorite data structure, because it always takes a long time to do this. And it's very easy to get it wrong. But we'll do it. We'll do it, but not today. All right, that'll be it. I'll see you guys tomorrow. Adios.